Hey y'all, welcome back. On today's lesson, we really didn't go over anything new. We are just continuing to work with these separable differential equations, and we're really just getting some practice in because the algebra can be a little intense on some of these problems, and it's just worth the time, I think, to practice solving these. So when the AP test comes around, you feel confident and you're able to solve these yourself. So number 1 says, consider the differential equation. And then part A says, on the axis provided, sketch a slope field for the given differential equation at the 9 points indicated. So basically what we're going to do is we're going to compute the slope for each of those 9 points. And those 9 points are as follows. We've got negative 1, 1, which is that top left point. We've got negative 1, comma 0, negative 1, comma negative 1, 0, comma 1, 0, comma 0, 0, comma negative 1. Let's see here, 1, 1, 1, 0, and 1, negative 1. And we're going to plug each of these into the slope equation. Remember that dy dx, that's the slope. And then we're going to try to sketch just like a little tiny line at each dot, at each point, to represent the slope of the solution to the differential equation that passes through that particular point. So at negative 1, 1, we're going to plug in x here. Okay, we'll plug in x here. We're going to plug in y here. Oh, it looks like I was a little offset there. I'm not going to plug it into pi, obviously. We're going to plug that into x. Okay, so negative 1, 1. So I'm just going to kind of plug these in and simplify as I go here. So if I plug in 1 into y, I get 1 minus 1, which is 0. And then actually I don't even have to go any further because 0 times anything is 0. So at negative 1, 1, we have a slope of 0. And that's going to be a little horizontal line here. At negative 1, comma 0, I'm going to plug in 0 into y. 0 minus 1 is going to be negative 1 squared is 1. And then cosine of 0 is pi times, cosine of negative 1 pi, so that's cosine of negative pi, is going to be negative 1. So 1 times negative 1 is negative 1. And so we should have a little slope kind of angling downwards like that. At negative 1, we get negative 1 minus 1, which is actually negative 2, and negative 2 squared is 4. And then cosine of pi times negative 1, we're going to get cosine of negative 1 again, which is negative 1. So 4 times negative 1 is going to be negative 4. Now on these problems, as we go through these, you really don't need to show all your work. So I'm just kind of erasing this as I go. We just really want to make sure that the slopes are reasonably, that they reasonably represent the slope that we're writing down. So if x is 0, then right here we have cosine of 0, and that's going to be the case for all of these. And cosine of 0 is 1. So we really just need to worry about plugging in that y, because anything times 1 is just going to be itself. So 1 minus 1, that's just 0. So this is going to be 0 here. Oops. And so at 0, comma 1, that's going to be 0. At 0, comma 0, 0 minus 1 is negative 1. Negative 1 squared is positive 1. So my slope should kind of angle up like this. And then at 0, negative 1, if I plug in negative 1 into y, I get negative 2 squared again, which is positive 4. So I have positive 4, something like this. Okay. There we go. Let's write that down. At 1, comma 1. So if I plug in 1 into x, I'm going to get cosine of pi. And just like we had before, cosine of pi is going to be negative 1. So for all of these, the cosine of pi times 1 is going to be negative 1. So you have negative 1 times 1 minus 1, that's 0 again. And I should have been able to pick up on that earlier, that if y is 1, then the whole thing is going to equal 0, because we're going to have 0 times cosine. And then, so let's see, the next one, if I plug in 0 into y, 1 squared is 1. 1 times negative 1 is negative 1. And then finally, at 1 comma negative 1, we already know what happens when we plug in 1 into x. That's just that cosine factor is going to equal negative 1. But if I plug in negative 1 into y, I get negative 1 minus 1, which is negative 2. Squared is 4. So I have 4 times negative 1, which is going to be negative 4. So we get a slope kind of like we have, or should be exactly like what we have at negative 1, negative 1. Okay, B says there's a horizontal line with the equation y equals c that satisfies this differential equation. Find the value of c. Now, to have a horizontal line, that means that the slope of that function, which is y equals c, is going to be 0. So slope equals 0. And so we've got this equation y equals something, and we can actually see it pretty clearly just in the slope field we created. We can see that horizontal line right here. So it's just going to be y equals 1. Okay, so the c value is 1. Yeah, that's pretty much it there. Another way that you can think about this is because we have to have a slope of 0, we need to know which value of y here is going to make the whole thing 0. And we found that earlier as we were constructing the slope field that is, in fact, 1. Okay, part C says find the particular solution to the differential equation with the initial condition f of 1 equals 0. So here we're actually going to have to solve for y. So I'm going to rewrite this differential so I can scroll down. dy over dx equals y minus 1 squared times cosine of pi x. So that's our differential equation that we're trying to solve. And so first I want to separate the variables. I'm going to bring my y's over to the left, and I can do that by dividing both sides by y minus 1 squared. So I'll have y minus 1 to the negative 2 dy, and I can multiply that dx over to the right-hand side. Now I want to integrate both sides, and I'm going to have to do a u substitution on both sides here because both sides are composite functions. So I'm going to split this up and do a little u substitution, probably continue it over on the right-hand side. But for the left-hand side, we've got u as y minus 1, which means du is just 1 dy. Oh, that works out nicely. We actually don't even need to modify the du. Usually we do, but in this case we do not. So yeah, we're going to make these substitutions to get an integral of u to the negative 2 du, and we can use the anti-power rule to evaluate that. Which would be u to the negative 1 divided by negative 1, and then we would have a plus c, but we know we're going to move that over anyway. So yeah, we're kind of ready to go back to x's and y's here. Since u was y minus 1, it's going to be negative y minus 1 to the negative first power. And then we will have that plus c, although we'll combine it just on the next step here. Okay, so on the cosine front, we've got a u that is pi x, so du would be pi dx, and we don't have an extra factor of pi, so we need to divide that on both sides. 1 divided by pi du is dx. So we're going to have the integral of cosine u times 1 over pi du. And integrating cosine is just going to give us sine, so we've got 1 over pi times the sine of u plus c, and replacing the pi x back in for u, we're going to get 1 over pi sine of pi x plus c. Now we're going to combine the c's, we're going to subtract that left-hand c, and those c's technically are different. They're not necessarily the same, but we're going to combine them anyway. So we're going to subtract that left-hand c over to the right-hand c and just combine it into a new constant. And so our equation after doing that is going to be negative y minus 1 to the negative 1 equals 1 over pi sine of pi x plus c. Now, one last thing I'm going to do here before I start trying to find my c is I'm going to multiply both sides by negative 1 because ultimately I'm trying to isolate y here. So I have negative 1 over pi sine of pi x plus c. And this is going to be the equation that I use for finding c. So I'll come back to that, but let's isolate y while we're here. So we're going to get rid of that power of -1, we're going to raise both sides to the -1. And that works because whenever you raise a power to a power, you multiply those powers, and -1 times -1 is 1. So we get y minus 1 equals -1 over pi sine of pi x plus c, all that to the -1st power. And then we need to add 1 to both sides. So here's our general solution. Y equals -1 over pi times sine of pi x plus c plus 1. Oh, forgot the little -1 power there. Okay, so we've got the general solution, but we're interested in the particular solution that satisfies, or that passes, where the function passes through the point 1, 0. So I'm going to go back to this equation up here, plug in 1 for x, 0 for y, and see if we can't get c. So if I plug in 0 for y, I'm going to get 0 minus 1 is -1. So -1 to the -1st power equals 1 over pi times sine of pi x. Now, if x is 1, that's just sine of pi. And sine of pi, let's see, what would sine of pi be? That's just going to be 0, isn't it? So this is just going to be c. So yeah, -1 to the -1st power is really just 1 over -1, and 1 divided by -1 is just -1. So we have -1 is c. And now we're ready to write our final answer here. Y equals -1 over pi sine of pi x minus 1 to the -1st power plus 1. All right, let's take a look at number 2. Of the following, which are solutions to the differential equation? Okay, so basically what we need to do is we just need to test each one of these by finding both the first derivative and the second derivative. So we really have like 3 problems in one here, and just see if whether or not they satisfy that equation. So let's start with the first one. So if that's y, then y prime is going to be, now the derivative of cosine is negative sine. So we have 5 times negative sine. So I'm just going to put the negative out here. Sine of 2x, and then using the chain rule, we're going to multiply by 2. And I might as well just combine it all at this point. 2 times -5 is going to be -10. So there's y prime. And then if I want to differentiate that again, y double prime is going to be -10 times the derivative of sine, which is cosine, so cosine of 2x. And then using the chain rule, we're going to have to multiply by the derivative of 2x, which is 2. So that -10 is going to become a -20. All right, so that's for the first one. For the second one, y prime is going to be 2e to the x. And y double prime is going to be, well, 2e to the x again. So that's pretty nice. Now, for part 3, it says c is a constant here. So for this one, y prime is going to be c times, and we're going to have to use a little chain rule here because that exponent is 4x, so we do have a composite function. So normally when we differentiate or really integrate e to the x, we just get e to the x. But when we try to differentiate e to some function in terms of x, then we need to multiply by the derivative of that expression. So in other words, long story short, we got to multiply by 4. So we're going to have 4c e to the 4x, and then y double prime will be 4c times, and then we're going to have another 4, so 16c e to the 4x. Okay, so now we're ready to start testing in that equation and see if when I plug in y double prime and y prime, does it equal 0? So for the first part, we've got y double prime, so that's -20 cosine of 2x minus 5 times y prime. So 5 times y prime would be 5 times -10 is going to be, so see, we got -5 times -10, that's going to be positive 50 sine of 2x plus 4 times y. So 4 times 5 is 20, so 20 cosine of 2x. Now, does that equal 0? Well, we get the negative 20 cosine 2x to cancel out, but then we're stuck with that 50 sine 2x, and that is not always equal to 0. I mean, it certainly could be for some values of x, but it's not for all values of x. So we know that 1 is not going to be an answer here. So we can eliminate all of our answer choices that have 1. So it can't be A and it can't be D. So now let's test 2. So here we've got y double prime again, which is going to be 2e to the x minus 5y prime. So 5 times 2 is 10, so minus 10e to the x plus 4 times y. So 4 times 2 is 8e to the x. And, I should have said that doesn't equal 0 on the top one. Now this is going to equal 0, because we can see we got the 2e to the x plus 8e to the x is going to be 10e to the x, and 10 minus 10 is 0. So this one does actually check out. So we're good with that one. We know it's going to have to at least have 2, so we can eliminate choice C. So really, we just need to check the last one here, and distinguish between choice B and choice E. So for this one, we've got y double prime, which is 16c e to the 4x, minus 5 times y prime. So 5 times 4 is 20, so minus 20c e to the 4x, and then plus 4 times y. So 4c e to the 4x. Does that equal 0? Well, we have the 16c e to the 4x and a 4c e to the 4x. Though 16 plus 4 is 20, and 20 minus 20 is 0. So this one works also. So after all that, this was kind of a long problem because it's really like 3 problems in one. We got our answer, which is E. Okay, on the second page here, we're just going to solve a few more separable differential equations here. For number 3, we can separate the x's from the y's by first dividing both sides by y minus 2 and then multiplying both sides by dx. And that's going to leave us with y minus 2 to the negative first power dy equals x squared plus 1 dx. Now, we will have to do a little u substitution on the left-hand side here when we integrate, but we won't have to worry about a u substitution on the right-hand side because we do not have a composite function over there. So for this one, maybe I'll just write it up here. If u is y minus 2, then du is 1 dy. So we actually get a perfect match here. We do not need to modify that du. And so this integral is going to be the integral of u to the negative 1 du, which is the natural log of the absolute value of u plus c. And u in this case is y minus 2. So we get the natural log of the absolute value of y minus 2. And I'll just leave the plus c out for now because I'm just going to move it over to the right-hand side. The integral of the right-hand side is going to be 1/3 x cubed plus x, and then we'll put the c right there. Now, this is going to be the equation we use to find c, because the next step, we're going to have to exponentiate both sides, and if we were to use that equation, we just have to go back and take a logarithm of both sides and end up back here anyway. So just make a note that we are going to come back to that equation. So yeah, if we're going to solve for y, we need to exponentiate both sides, and that gives me the absolute value of y minus 2 equals e to the 1/3 x cubed plus x plus c. And then trying to get rid of that absolute value, we need to throw in a plus or minus onto e. So y minus 2 equals plus minus e to the 1/3 x cubed plus x plus c. So we need to decide if it's going to be plus or minus. And if x is 0, then y is 5. So we are going to go with the plus. Okay, so we're going to choose plus. Get rid of that minus. All right, the last thing to do is going to be to add 2 to both sides. So get y equals 2 plus e to the 1/3 x cubed plus x plus c. So we're almost there, but we need to find the c. So let's do that. All right, if I substitute in 5 for y and 0 for x, I'm going to get the natural log of 5 minus 2 is 3 equals 1/3. Now, x is 0, so this is just going to equal c. So we have 0 plus 0. So yeah, c is just the natural log of 3. You can actually drop those absolute value bars and just put regular old parentheses because the absolute value of 3 is 3. So now we're ready to write our final answer here. Y equals 2 plus e to the 1/3 x cubed plus x plus the natural log of 3. Number 4, if you see y prime or f prime or anything like that, I would just right away go ahead and rewrite that y prime as dy dx. And so to separate the variables, we're going to divide both sides by y and multiply both sides by dx. So we can get y to the negative 1 dy equals x dx. And then we'll go ahead and integrate both sides. So the integral of y to the negative 1, no u substitution or anything required here. It's just going to be the natural log of the absolute value of y equals x squared times 1/2. So this is going to be the equation that I use to solve for c. And yeah, we want to exponentiate both sides here. So I get the absolute value of y equals e to the 1/2 x squared. And then we need to get rid of that absolute value. So I have y equals plus minus e to the 1/2 x squared. But I know that one of my outputs has to be positive. So I'm going to choose plus and get rid of that minus. Oh, wait, I forgot the plus c on there. My bad. And then, yes, let's go ahead and find that c. We'll do that right over here. Plugging in 5 for y is going to give me the natural log of 5, kind of like we had in the last one. And yeah, that's going to equal, if we plug in x for 0, that's just going to be c. So my answer here will be y equals e to the 1/2 x squared plus natural log of 5. Now, one thing I want to point out on these particular problems, and this might be, I think this is worth noting here, is sometimes you'll see these answers written a little differently if it's a multiple choice question. If it's free response, this is perfect. But if it's not, you might see, like this last problem, you might see the answer written like this: y equals 5 times e to the 1/2 x squared. I want you to think about, like, how would that, like, algebraically, how do we get there? So basically what you could do, and this is not something you have to do on a free response, but you might have to be able to recognize this on a multiple choice, is we can actually rewrite that expression. I'll kind of let me erase this so we can see how we get there. Is y equals e to the 1/2 x squared power times e to the natural log of 5. And that's because whenever you multiply powers with the same base, you can add the exponents. So you could follow that property backwards to kind of split up. When you have a power that has a sum in the exponent, you can split that up using multiplication, using that power property backwards. And then e to the natural log of 5 is just 5. So this is going to equal 5e to the 1/2 x squared. So this would be like kind of an alternate correct solution, and you might just this is kind of it's not going to happen that frequently, but if it comes up, I don't want you to be totally confused when you don't see your answer in the multiple choices. We can see that, like, that's going to happen over here too. We could rewrite this as y equals 2 plus. I'm going to give you a minute to think about what this, what the answer to this is going to be, kind of similar to the last one. So just think about that for a minute. And then hopefully you realize that, hey, we could split that up like we did the last one, and this natural log of 3, e to the natural log of 3 is just 3. So this could be written as 3 times e to the 1/3 x cubed plus x. So just a little, side note here that there is sort of an alternate correct answer that you might see in a multiple choice setting. Let me move these so they don't get in the way of the neck. How am I going to do that? I'm just going to have to rewrite it, I think. I'll just delete all this. You might see that in a multiple choice setting. So just be ready for like anytime if you feel like you've worked it out correctly, but the answer choice is just not looking exactly right. Probably that's what's going on here. So like this one, the alternate solution would be 2 plus 3 times e to the 1/3 x cubed plus x. And an alternate solution for this next one would be y equals 5 times e to the 1/2 x squared. It is a little bit more compact there, so you might consider it like maybe more simplified. But again, not a huge deal, especially for free response questions. But just want to throw that out there. For number 5, finding an integral. Okay, well, this is going to be something that we're probably going to want to use a u substitution on. We're going to split up that integral, say the integral of 5 times e to the 2x dx plus the integral of 1 over x dx, and just to kind of evaluate these separately. So for the first one, we are going to have to use u substitution, okay, where u is 2x. Okay, so if u is 2x, then du is 2dx, but I have 5dx, so I need to divide both sides by 2 and multiply both sides by 5. So 5 halves du is the same thing as 5dx. Okay, so when I do that u substitution, I'm going to have the integral of e to the u times 5 halves du, and the integral of e to the u is just e to the u. So I have 5 halves times e to the u plus c. E to the u, since u is 2x, is going to be e to the 2x. So that first integral is going to be 5 halves e to the 2x. And then we have plus that second integral, which is just a basic transcendental that you should know by now, is the natural log of the absolute value of x. And then we have plus c. So it looks like, what's our answer going to be here? Looks like it's going to be B. All right, number 6 says g is a continuous function. Using the substitution given, okay, u is 2x minus 1. What is this definite integral equal to? So when we make that u substitution, kind of the tricky part about these kind of multiple choice items is you have to make sure you also change the bounds. So I can rewrite this as the integral of, well, we don't want to do 3 and 2, of gu, and then hang on, if u is 2x minus 1, then du's got to be 2dx. I don't have a 2dx, so I need to divide both sides by 2 to make that substitution work. So I've got gu times 1/2 du. Okay, and I actually don't have to go back and change everything back to x's, because if you look at your answer choices, they're all in terms of u. One thing I do need to do, though, is modify the upper and lower bounds, because those are x values initially, and we need to change them to u values. But since u is 2x minus 1, this upper bound 3, 2 times 3 minus 1, is going to be 5. And the lower bound, 2 times 2 minus 1, 4 minus 1, is going to be 3. So this is what we're looking for as far as the answer choice goes, and I do see that is choice D. Number 7, determine the following integrals. So just some more u substitution practice here. For this one, I'm going to let u be 3x squared, because that's the inside function. And then so du would be, what would that be? 6x dx, although I have 2x dx, not 6x dx, so I need to divide both sides by 3. So 1/3 du is 2x dx. Now I'm ready to make that substitution. So I have the integral of sine of u times 1/3 du. So that'll be 1/3 times the integral. Oh, actually, we can just go ahead and integrate that, right? We know the integral of sine. Since the derivative of cosine is negative sine, the integral of sine is going to be negative cosine. So let me throw in a negative sign out front of that. Negative 1/3 cosine of u plus c. So since u is 3x squared, my answer here should be negative 1/3 cosine of 3x squared plus c. Don't forget that plus c on any indefinite integrals. Okay, for part B, what do we have here? We've got the integral of sine cubed 4x times cosine of 4x. This one might be a little tricky at first, but notice how cosine is the derivative of sine. So what if we let, what do we want to do here? We want to let, if u, all right, well, hang on. I'm looking at this again, and I'm noticing that we do have a composite function, but we actually have a triple nested composite function because we've got 4x, and then we've got sine of 4x, and we got all that cubed. So I think what we want to do here is let sine be, or u be sine of 4x, because that's the inside function of that, x cubed. So if u is sine of 4x, then du would be cosine of 4x times the derivative of 4x, which is going to be 4, dx. Now, I don't have 4 cosine 4x dx. I just have cosine 4x dx, so we'll have to divide both sides by 4. So we get 1/4 du equals cosine of 4x dx. And now I'm ready to make my substitution. So I've got the integral of, now u is sine of 4x, so I have u cubed, and then times 1/4 du. So yeah, we can integrate that one. We just use that anti-power rule and raise that power to a power of 4. We've got 1/4, and we actually have another 1/4 there. So we got 1/4 times 1/4 times u to the 4th, and then plus c. And since u is sine of 4x, we can go ahead and write our answer here. 1/16 times sine of 4x, all that to the 4th power, which is, I already wrote that, plus c. Okay, well, we've got one last page here, and this problem came from an old AP test from 2022. So as of the recording of this video, that was 3 years ago. It says, consider the differential equation, dy dx equals 1/2 sine of pi over 2x times root y plus 7. Let y equals f of x be the particular solution to the differential equation with initial condition f of 1 is 2. So there's your point, and here's your slope. Part A says a portion of the slope field is given below. Sketch the solution curve through the point 1, 2. Okay, so 1, 2 is labeled there, and basically you're just going to follow the slopes, okay? And it looks something like this kind of looks good. I think it should be not too hard to come up with this. It's just supposed to be kind of a general sketch here. You don't have to be super accurate about that. Okay, so what does that look like? That to me looks like a negative cosine graph, right? It's just negative cosine shifted up, and is there even, I don't even think there's going to be an amplitude other than 1. I don't think there's a vertical stretch, but it's a little hard to tell. We don't know for sure. We might need to do a little digging to figure out exactly what's going on there. So, if I had to guess, I would say that this, the solution here that goes through that point, again, if I just had to guess, would be negative cosine x plus 2.5, I guess. I don't know. That's just kind of a guess there, but let's see. B would be, it says write an equation for the line tangent. Okay, so we're actually going to come up. Oh, no. First, we're going to find the line tangent. Okay, so I'm getting ahead of myself. We want to find the line tangent to the solution curve in part A. So basically what we want is the equation of this line right here. Okay, so y-intercept should be like, I don't know, looks like roughly a half, and slope should be, looks like about 1. So that's kind of what I'm expecting here, is maybe like 1/2, or sorry, 1x plus a half, something like that. But let's actually do the math and figure out what it is. So we have a point, 1, 2. We do need to find the slope there, so we're going to have to plug in 1, 2 into our slope equation. Okay, so my point is 1, 2. My slope, we're going to have to compute that. It's going to be 1/2 times the sine of pi over 2 times 1. Okay, so sine of pi over 2 is 1. So I'm actually just going to back this up and just say that's times 1 times the square root of 2 plus 7 is 9. So we've got square root of 9 is 3, and so we get 3/2. So I was a little bit off on the slope there. It's 3/2, it's not 1, but that's okay. So y minus 2 equals 3/2 times x minus 1. So that's going to be the linear function. You know, this is just a rough sketch, but it's going to be something like this. That y-intercept, by the way, looks like it's, let's see, 3/2 times -1 is -3/2 plus 2. So the y-intercept actually is 0.5. Okay, so I was right about that. Okay, so yeah, let's go ahead and estimate the value of the function at 0.8. So notice here at 0.8, which is like rough. Oh, okay, we're all over the place here. Let's zoom back here. Get this so we can actually see everything. So 0.8 is like right here, and so we're estimating this point. And so we can just see visually it's going to be like 1 point something, maybe like 1.6, 1.7, 1.8, something like that. And the tangent line is going to be a pretty good approximation. Remember that these tangent line approximations usually work really well as long as it's around the point that it's where the line is tangent to, that point of tangency. Now, if we were to try to use this to estimate like f of 3, well, this line is going to be way over here, and the value of the function is like not even close. So make sure that if you're using this tangent line approximation that you're using x values that are close to the point that we know. Okay, so we've got y minus 2 equals, I'm just going to write this as 1.5 because we're dealing with decimals here, 0.8 minus 1. Now 0.8 minus 1 is negative 0.2, and 1.5 times negative 0.2, well, 2 times 1.5, that would be 3, so this would be negative 0.3. And then if I add 2 to both sides, I'm going to get my estimate here, which is 1.7. So we can say then that f of 0.8, based on our linear approximation, should be approximately 1.7. And here was our actual tangent line that we got initially. Okay, part C says it is known that the second derivative is positive in between x equals -1 and 1. And that makes sense. Like, take a look at what's going on between -1 and 1. And what does it mean for the second derivative to be positive? It means that the graph is concave up. And we can see based on our sketch here that, yeah, it does look like the graph is concave up between there, doesn't it? Right? I mean, obviously, well, maybe not obvious is a bad word to use here, but it does appear as though in that interval between -1 and 1, that red curve that we have drawn is concave up. So it says, is the approximation for part B an overestimate or an underestimate for 0.8? Now on this sketch, it's a little hard to tell, but let me just give like a more exaggerated sketch here. If we have a concave up curve, and we've got a point on that curve where we have a point of tangency, all the points on that line are going to lie below the curve. Okay, so that means that we have an under approximation. Okay, so f, let's say it like this. 1.7 is an under approximation because f is concave up. since f double prime is positive. And that's about it. That's really all you need to say. Part D says use separation of variables to actually find y equals f of x. So, yep, we're just going to solve yet another differential equation. And if you're feeling pretty good about this page, then you should feel pretty good about going into the AP test because, this is kind of the difficulty level of the problems that you can expect to see. Okay, so let's go ahead and separate those variables out. We need the y's over to the left, so I'm going to have actually that square root of y plus 7. I'm going to be thinking about that as like y plus 7 to the 1/2 power. So that when I divide both sides by that expression, that's going to become y plus 7 to the negative 1/2 power dy equals 1/2 times sine of pi over 2 x dx. All right, well, we need to integrate both sides, don't we? And we're going to have some u substitutions to deal with. So, yeah, let's do it. Or you could say, let's do it. All right, that's okay. That's enough of that. So, yeah, let's split this up and just kind of treat these as separate problems here. So over here, we're going to let u be y plus 7, which means du is just 1 dy, and we get a perfect match there. Beautiful. Integral of u to the negative 1/2 du. So the integral of u to the negative 1/2 is just going to be 2u to the positive 1/2. So 2 times the square root of u. And yeah, let's go ahead and actually, let's wait. Let's do the right-hand side, and then we'll put our u's back in, or our x's and y's back in, and actually write the equation that we get after the integration. So for this one, we are going to let u be pi over 2x. So du is pi over 2 dx. Now, I don't have pi over 2 dx. What I have is 1 over 2 dx. So I need to divide out that pi. Get 1 over pi. 1 over pi du is 1 over 2 dx. So now I've got the integral of sine u times 1 over pi du. What's the integral of sine? Let me think. So the derivative of cosine is negative sine. So the integral of sine has got to be negative cosine. So we're going to have negative 1 over pi cosine of u plus c. All right, so let's go back and rejoin this these expressions. I'll just continue up here. Okay, so we've got 2, and then on that left-hand side, u was y plus 7. So actually, you know what? I'm not going to do the 1/2 power just because I think the arithmetic will be easier in our head if we write this as square root of y plus 7. That is to the 1/2 power. And that equals negative 1 over pi times cosine of pi over 2 plus c. Then I'm going to multiply both sides by 2. And you guys know the drill here. These equations look a lot scarier than they really are as long as you're practicing enough of these. Okay, now this is probably going to be the equation that I want to use to solve for c. So I'm going to put a little star by it because the next step is going to require that I square both sides. Yeah, so let's say the y plus 7 equals, and then we get this lovely expression, negative 2 over pi. Oh, wait, hold up here. We didn't multiply both sides by 2. We were supposed to divide both sides by 2. Oh, my goodness. Sorry, y'all. Let's fix that. So that should be 1 over 2 pi, not 2 over pi. Let me clean that up, make it a little easier to look at. So negative 1 over 2 pi cosine of pi over 2 plus c. We're going to square it. That's what we wanted to do on that step. We want to square both sides. Next, we're going to subtract 7 from both sides. So now we've got y equals negative 1 over 2 pi times cosine of pi over 2 plus c, all that squared, minus 7. So now it's time to figure out what that c value is. I'm going to use that start equation, this one right here, and plug in my initial condition here that f of 1 is 2. So let's see. Let's see if we can't do this. I'm just going to work this out, maybe in a different color right below here since I'm kind of out of space. But if y is 2, we have 2 plus 7. That's 9. Square root of 9 is 3. So 3 equals, and then we have negative 1 over 2 pi. I've got a feeling this is going to work out nicely. Hang on. Before I write all this, cosine of pi. Wait a minute. I'm missing an x. Oh, goodness. We got to go back and throw in an x here. I'm like, where am I going to plug in the x? Yep, another mistake, Mr. Schuler. You're slipping. All right. So, yeah, plugging in 1 into this cosine function here, we've got pi over 2 times 1, that's pi over 2, and cosine of pi over 2 is actually 0. So 0 times anything is just 0. We actually don't need this negative 1 over 2 pi because it's just going to be equal 0. So 3 is C. And so we've got y equals negative 1 over 2 pi times cosine of pi over 2x. Don't want to forget the x there. We got the plus c now. All that will be squared, and then finally minus 7. There you go. Okay, that's it for today, y'all. We've got one more day where we're going to practice separable differential equations. We're going to look at some application problems where you can solve them using this method of solving differential equations. I think you guys are going to like it. So anyway, that's enough for today. You'll have a great day. I'll see you next time.